Hey, hello and welcome back everyone. Moving on to section 1.3, title is Matrix and Vector Products. We're going to primarily be talking about matrix-matrix multiplication and eventually matrix-vector multiplication in this video, and we'll reserve vector-vector multiplication to the next video because there's quite a few of those that will probably deserve their own video. Starting out with matrix-matrix multiplication, I wanted to start here because this is the multiplication that most directly corresponds to what we were studying the last time when we defined the linear algebra as the mathematical algebra. And let's recall that a mathematical algebra is a group of objects which remains under a plus and times, so an addition and a multiplication. And so it's this algebra formed from sums of linear functions and compositions of linear functions, where the sums are naturally still going to be our addition, but compositions, which normally we notate with the circle, turns into our multiplication, which we notate with a dot, or sometimes just concatenation, meaning placing two objects next to each other. And so how are we going to end up defining something like a matrix product, or in other words, a matrix multiplication? We recall matrices, right? Like 2, 3, 1, negative 1, 0, 2, 2, 2, negative 1. If we were to multiply two matrices, maybe 0, 1, 2, 2, 3, negative 1, 1, 0, 1. If we were to multiply the two of these, somehow we want that multiplication, we want this to capture the action of function composition. So even though we're calling it a multiplication here, we want it to capture the action of a function composition. And so how do we actually define it? We define the multiplication of two matrices mf1 and mf2, and I'm just using those subscripts f1 and f2 to describe the functions that they represent, because every matrix represents a function. We're going to define their product. So mf2 times mf1, that's at the bottom of the screen. We're defining the product, and recall this is my definition equal sign. Define it to just be the matrix which represents the function, which is the composition f2 composed with f1. So we just define a matrix multiplication to be the representation of the composition of the two functions. And so let's go through one example of this matrix product directly from the definitions, and then we'll end up seeing maybe how we should actually compute it in a later example, because the definition example just helps us understand really what's going on behind the scenes before we actually try to compute these in slightly an easier fashion, but that easier fashion sometimes masks what's actually happening behind the scenes. So let's go by definition right away. We've got two functions here, f1 and f2, and let's go ahead and construct the matrix representations of these functions. Notice the output of f1 here has the coefficients 1, 1, 1 against x, y, and z in the first output, and so we've got 1, 1, 1 there for the first row of its matrix representation, and then the second output is really 0x plus 2y minus 1z, and so the coefficients here are 0, 2, and negative 1, which enter into the second row of the matrix representation of f1. We represent f2 using a matrix as well. Let's just be a little careful that the input now is just two-dimensional, and so we're only going to require two columns in the matrix. Two columns in matrix, rather than the earlier three columns in f1 corresponding to R3. Now we have two columns in the matrix. Our first matrix will have a coefficient of 1 and a coefficient of 2, so that's happening in the first row, and then the second row will have a coefficient of 3 and a coefficient of negative 3. Okay, so let's see if we can compute the matrix multiplication mf2 with mf1 directly from the definition. To do that, we're going to have to compute the composition of f2 with f1, which means we're going to take the entire output of f1, which is right here. We're going to take this entire output and we're going to plug it in to f2. So there I've taken the entire output of f1 and plugged it into f2. And then now that we're working with f2, this entry x, we don't want to think about it as the entry x anymore. It's the entire term that's going into the entry of x. So I'm taking x plus y plus z, and I'm substituting that in for both of my copies of x here. So I'm going to substitute that in. And then for the second input here, 2y minus z, I'm going to substitute that in for the second entry there. So this y and this y are both going to substitute in 2y minus z. So you can see exactly that happening here. So this x becomes x plus y plus z. There it is. and this x also becomes x plus y plus z. There it is. And then this y becomes 2y minus z. There it is. And this y also becomes 2y minus z. There it is. So I'm going to substitute all of those terms in, and then I'm going to go ahead and simplify. So simplify. I'm going to simplify here. I'm simply going to expand all of these multiplications, and then I'm going to combine my like terms. So there's me expanding, and then here's me combining like terms. What we end up with is a function that maps x, y, and z to x plus 5y minus z, 3x minus 3y plus 6z. Well, you'll notice, what did we get out of this composition is we got a linear function, and so there is a matrix representation. How do I find the matrix representation of this output? Well, I'm just going to look at coefficients. My coefficients are 1, 5, and -1 in the first row, and I have coefficients 3, -3, 6 in the second row. And so that matrix representation of the composition of functions is how we define the multiplication of these two. Define multiplication. And so we would just write out directly, how do I multiply the matrix 1, 2, 3, 3, -3 against the matrix 1, 1, 1, 0, 2, -1. You multiply that by performing the function composition and then reconstructing the matrix representation of the function composition. That's how we define two matrices to be multiplied. However, that is not how we choose often to compute matrix multiplication. So I have a proposition here. It's a proposition because this is no longer a definition. This is now a result of the definition. How do we actually multiply two matrices if I don't want to go through the process of function composition? So this is avoiding function composition. Even though it's behind the scenes, we can avoid function composition by computing this. And I know this looks absolutely atrocious. You've never seen so many sigmas in your life. Probably neither have I. And so we're going to go a little bit below to here where I say, from a more visual approach, how do we actually perform a matrix multiplication? So I've got my matrix here on the left. I'll call this left matrix. And I've got my matrix here on the right, which I'll call right matrix. How do I perform the composition? What I'm going to do is I'm going to select a row from the left matrix. So for example, I've chosen the jth row here, and I've kind of isolated it with its own color. And I'm also going to select a column from the right matrix. Now this is very important. You want to remember the order row, column, row, column, row, column. It shows up all the time. Rows happen to be on the left, columns happen to be on the right. And once I've selected my row on the left and my column on the right, what do I actually do? I multiply each entry of the selected row with each respective entry of the selected column. In this sense, I'm taking the first entry of my row, multiplying with the first entry of the column. That's this term here. I'm taking the second entry of the row, the second entry of the column, that's this term here, and eventually the last entry of the row and the last entry of the column, that's that term there. And I finish by adding all of those terms together. So I'm just going to go through, I'm going to say plus, 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 and I'm going to add all of these multiplications together. Of course, if I'm performing a lot of multiplications and a lot of additions, the answer here will just be a number. What do I do with that number once I've finished? Right, I've selected a row and a column. What should I do with that number? I'm going to take that number and I'm going to place the value in the position of the overlap between the row and the column. So if I scroll back up and I say, I selected this row and I selected this column, I'm going to ask the question, where do they overlap? And once I answer wherever they overlap, it's going to be in the future matrix that I'm constructing later, that's where I'm placing the result. So the result here, if I had the jth row and the kth column, the result gets placed in the jth row and the kth column of the answer matrix. So this very last matrix is going to contain that jth row, kth column element. I'm going to repeat all these steps until all possible row-column combinations are computed. Now, what this means, right here, this is why actually matrix computations are computationally intensive. I'm talking from a computer science standpoint. Matrix multiplications are computationally intense. So in this sense, like a lot of computer scientists try to, there's a lot of algorithms based on what is the minimum number of computations we have to do to find matrix multiplications. It turns out it's fewer than you would necessarily expect if you just followed this procedure, but when we do it by hand, we're basically always going to be following this procedure, which is just looking at all combinations. Now, even that is a little bit abstract of a computational technique. Let's just go through a few examples. It ends up getting quite a bit easier once you get used to it with examples. So I'm going to try to multiply the two matrices here. So I've got 1, -1, 0, 3, and 2, 2, -2, 1. And if I want to compute the matrix multiplication of these two matrices, what I'm going to do is I'm going to turn everything on the left into rows and everything on the right into columns, and then I'm going to consider all possible combinations of rows and columns. So let's just consider the first combination of the first row against the first column, and I've drawn that below here as 1, -1 against 2, -2. And how do I actually perform the multiplication? Well, I grab the first entry and the first entry, that's a 1 and a 2, and I multiply them. And then I grab the second entry and the second entry, that's a -1 and a -2, and I multiply those, and then I add everything together, I end up with a 4. And so the first row against the first column gave me a 4. What do I do with that multiplication? Well, what's the overlap between the first row and the first column? They overlap in the top left entry. So once I know that they overlap in the top left entry, I say this answer 4 goes in the top left entry. 4 is going to go in the top left entry. I'm going to repeat this with the combination of the first row and the second column. So I'm going to take the first entry 1 times the first entry 2, and I'll take the second entry -1 times the second entry 1, and I'm going to multiply those together. I'll get a 2 and a -1, and then I add, and I get overall 1. Where did the first row and the second column overlap? Well, the first row and the second column overlap on the top right. And so now I'm going to take this answer of a 1, and I'm going to include it in the top right. That's what I have happening here. I've added the 1 into the top right. My -6, which results from the second row and the first column. Well, the second row and the first column will overlap in the bottom left because it's the second row and the first column. And then the second row and the second column, which is a 3, will overlap in the bottom right. And so the -6 is going bottom left, and the +3 is going bottom right. And so after I've computed all those combinations of 4, 1, -6, and 3, I can efficiently compute the matrix multiplication of 1, -1, 0, 3 against 2, 2, -2, 1, and I get 4, 1, -6, 3. I'm going to mention how I do this in my head now, because often as I've written everything out, it's quite tedious. And so if you want to save yourself a little bit of time doing this computationally, how do I do it all in my head? In my head, what I do is I say first row, first column, I'm going to take 1, 2, and multiply them to get 2. I'm going to take -1, -2, multiply them to get 2. I'm adding both copies of 2 in my head, and I'm getting a 4, and I just place the 4 in the top left. I then repeat this with the first row and the second column. I multiply the 1 and the 2 in my head to get 2. I multiply -1 and 1 in my head to get -1. I have the 2 from before plus the -1 in my head. I'm going to get a 1 in the overlap of those two, which is the top right. Then I'm going to take the second row and the first column. I'm going to multiply the 0 and the 2 to get 0, a 3 and a -2 to get -6. 0 minus 6 is -6. And then I take the second column and the second row and the second column in my head and multiply 0 on 2 and 3 on 1 to get 0 plus 3 gives me a 3 in the bottom right. So that's how I do it in my head. It goes a little bit faster if you want to do it that way. Otherwise, being quite methodical about it as I've drawn it out can be helpful. So I've got another example here, but I'll let you do that yourself. And then I do have a little bit more complicated example of a 4x3 and a 3x2 matrix, where now I'm going to compute every row here against every column here. And what are we going to get out of this? Let's just try to do it the fast way instead of the slow way. I'm going to take 1, 0, 1 against 3, 0, -1. Well, 1 times 3 gives me 3. 0 times 0 gives me 0. And 1 times -1 gives me -1. That's going to give me in total a 2 in the top left corner. So I'm going to replace that with a 2. If I do the first row against the second column, then I have a 1 times a 2 plus a 0 times a 1 plus a 1 times a 1. I'm going to have 2 plus 0 plus 1 gives me 3. I can then repeat with the second row times the first column. That's going to be -2 times 3 negative 1 times 0 and 1 times negative 1. So since negative 2 times 3 was negative 6 plus negative 1 times 0, we're going to add 0 to negative 6, still get 0, and then 1 times negative 1. We're going to subtract 1 from negative 6, recovering negative 7 in the overlap of those two rows and columns. I can then repeat with the second row against the second column to give me negative 2 times 2 is negative 4, plus negative 1 times 1 gives me to negative 5, plus 1 times 1 sends me back to negative 4. Then if I want to do the third row by the first column, we have a 1 times 3 is 3, plus 1 times 0 is still 3, plus negative 1 times negative 1 is going to give me a 4 in the overlap of the third row and the first column. Then I can take the third row against the second column, which is going to give me a 1 times 2, which is 2, plus 1 times 1, which is 3, plus negative 1 times 1 sends me back to 2. And then finally, I will do the fourth row against the first column, which will be 0 times 3 is 0, plus 3 times 0 is still 0, plus 0 times negative 1 is still 0. And so I will have a 0 in the overlap of the fourth row and the first column. And then I can do the fourth row and the second column with a 0 times 2 is 0, plus 3 times 1 is 3, plus 0 times 1 is still 3. So I will have a 3 in the second column, fourth row, where those terms overlap. So this will be my result of this matrix multiplication. Of course, if we scroll down, we see piece by piece exactly the matrix that we just constructed as the product of the two matrices. So in our last example, I do just want to stress that the order of matrix multiplication does matter. And this is directly dependent on the fact that, if I compose F1 with F2 is not the same as composing F2 with F1. In fact, one of these might even be forbidden if the dimensions of the inputs and the outputs disagree. So only one direction may be valid of the two of them. And so because matrix multiplication represents the composition of linear functions, it is completely dependent upon the order that the linear functions are composed in, and equivalently the order that the matrix multiplication is written in. If we decide to multiply the matrix on the right by the matrix on the left, then actually nothing can happen, right? Because what are we looking at here? We're looking at, if I take a row on each of these terms here on the left against the column here, if I look at the overlap of these two, well, I'm going to try to multiply the first entry by the first entry, the second entry by the second entry. All of a sudden, I run out of entries to multiply. So this is a forbidden operation. And it exactly corresponds to, two functions not being allowed to be composed with one another. But it's kind of important to note that you just can't perform, this specific. It has 3 rows and 2 columns, so this is a 3 by 2 matrix, and then this one has 4 rows and 3 columns, this is a 4 by 3 matrix. If you look at the 2 here and the 4 here, those numbers are not equal, and if those numbers are not equal, there's no way you're going to be able to multiply the matrices. And that directly corresponds to just composing two functions. If you decide to go in the reverse order, right, kind of the order that I decided to write them in, so if we put this one on the left and this one on the right, then we go ahead and look here, we have a 4 by 3 matrix and a 3 by 2 matrix. Because these 3's are equal to one another, 3 is equal to 3, when you perform the matrix multiplication, those are great, they're happy. In fact, they end up disappearing because you're adding all those terms together, and you end up with a 4 times 2 matrix at the end here. Now let's talk about a matrix vector multiplication, kind of the other way that we can interpret matrices as, of course, multidimensional linear functions. Vectors are going to be, as we define them, vectors are points, right? These are points in multidimensional space. And if we're taking functions here, it makes a lot of sense to think that, if I'm multiplying a function against a point in a space, the way we're going to end up defining these is these are going to be defined as an evaluation of the function at the point. So that's how we'll end up defining a matrix vector multiplication, and we see that in the definition right here. So given some multidimensional function f, linear, should be linear, so it has a corresponding matrix representation, which I'm calling m sub f. And suppose we also have a multidimensional point x that we're representing as a vector, of course I'm calling it x here, but you think about this as x1, x2, ... xn. So we have a vector here. How do we define a matrix vector multiplication? Well, the multiplication is written just like it would look like a multiplication. It's the matrix and then the vector back to back, but we're going to define that to just be the evaluation of the function at the point x. So rather than doing any sort of direct computation with the matrices and the vectors, we're going to do this indirectly, as I describe here. So we're going to do it directly from the definition. I have a function which is a linear function, and it has the coefficients 1, 1, 1. So those are going to be in the first row of my matrix. And then it has the coefficients really 0x plus 2y minus 1z. So the coefficients 0, 2, and -1 are in the second row. And then let's consider the vector 1, 2, 3 as the point, but also the vector 1, 2, 3. What would it mean to take this matrix and multiply this vector? Well, we're going to define it to be equal to just this function evaluated at this point. So how do I evaluate the function at the point? I just take my 1 and I plug it in for x. I take my 2 and I plug it in for y. And I take my 3 and I plug it in for z. And it turns out, well, what I get here, 1 plus 2 plus 3 is 6, and 2 times 2 minus 3 is 1. So this should be the point 6, 1, or in other words, the vector 6, 1, because it's still a point in R2, so a two-dimensional vector. So that's how we're going to define the matrix multiplication. So here I just say that this matrix defined to multiply this vector gives me the vector 6, 1. Now I want to mention really quick, if we take our previous computational understanding of a matrix multiplication and apply it here, we get the same answer. Right, there's a reason why we don't worry too much about when we consider a column array as either a vector or as a matrix, and the reason is that they kind of behave like the same mathematical object when they're represented in arrays. So let's go ahead and just consider this as a 3-row by 1-column matrix instead of as a vector. And let's think about what we get. Well, you take this row against this column, and you're going to multiply the first entry by the first entry to get 1, plus the second entry times the second entry. 1 plus 2 gives me 3, plus the third entry times the third entry. 1 plus 2 plus 3 gives me 6. And so that's exactly what we were doing with matrix multiplication earlier. We can do the same thing with the second row and the first column to get, well, 0 times 1 plus 2 times 2 plus -1 times 3 gives me 4 minus 3 gives me 1 as my answer. And so it really doesn't matter if you think about this product as a matrix vector product or as a matrix matrix product, you're going to be able to compute the answers in the exact same way. And so that's what I actually have in this proposition here, is to say everything that I've said in the last words, which is to say just that you can consider this vector multiplication really as a matrix multiplication and then apply everything we know about matrices to the matrix vector product. So I do have one example of that here. Let's just directly compute the matrix vector product, which is 3, 2, 0, 1, -1, 1 against 2, -1. How am I going to do that? Well, I'm going to split the left matrix into rows and the right matrix, which happens to be a vector, into its only column. And then my outputs are going to be, well, 3 times 2 is 6, plus 2 times -1 gives me 4. I then have 0 times 2, which is 0, plus 1 times -1 gives me -1. And then finally, I have -1 times 2 is -2, plus 1 times -1 is -3. So the output here is the vector 4, -1, -3. And let's go ahead and scroll down and see that indeed we recovered the vector 4, -1, -3 from a matrix vector multiplication. Anyway, we're going to stop there for today, just because the vector-vector multiplications can get kind of intense in some other definitions. But for now, matrix-matrix and matrix-vector multiplication, very straightforward as long as you do it with associating a lot of rows on the left and columns on the right, multiply and add all of the terms together. Anyway, I'll see you in the next one. Bye.